this video, we will talk about two problems. It is focused on the lowest common ancestor, LCA. So we have two problems. One is easy, the other is medium, but both of those problems are quite similar. So let's see. So first we have problem 235. So here we have a binary search tree. The other problem, we just have a binary tree, not binary search tree. But here we have a binary search tree. So here we have a BST. We just want to find the lowest common ancestor. So in this case, here the first node is 2, so 2 is here. Second node is here, 8. So their shared ancestor would be 6, and this is the lowest. Yeah. So let's say if P was say 2 and then Q is say 3. So in that case, what is the LCA? Well, the ancestor for 3 would be 4, 2, and 6. The ancestor for 2 would be 2 and 6. So yeah, so here you can, so here it says for some node to be descendant, it allows a node to be a descendant of itself. So it means that the ancestor for node 3 would be 3 itself. So 3, 4, 2, and 6. For 2, the ancestor will be 2 itself, so 2 and 6. Lowest common ancestor would be 2 in that case. The common ancestor would be 2 and 6, and then the lowest one would be 2. So that's the idea. Let's see. So how would you approach this problem? The hint is that this is a binary search tree, meaning that if, say we start at 6, if P's value is 2 and Q's value is 8, then for P, since it is less than 6, we can just go to the left subtree. For Q, we just go to the right subtree and go search in this tree. So for instance, if we have, say, P is equal to 2, Q is equal to 4, we only have to look for the left subtree. We don't have to look for the right subtree, so we just ignore this. So that's the first part. So that's the how you move your pointer, the root. Now the next problem is how do you return the value? How do you return the lowest LCA? In this case, say we have some trees all up here. I just imagine that you have trees like that's above here, above this node 6. Say we are at here. Now, so in this case, both 2 and 8, their common ancestor would be, the lowest common ancestor would be 6. So because P is in the left subtree and Q is on the right subtree, so if you look at here, both P and Q are on the same side. So here they are both on the left subtree, but here you have a split. So in this case, you return the root where the pointer is pointing at. So here we return root. Now, how about here? This case, so let's say we come down here and our root points to this node 2. Let's say P is 2. So we found P, and 4 happens to be here. Now, because 4 is bigger than 2, it is in right subtree. But we don't have to traverse this. We don't have to go to the, say, right subtree of this. We just return the root, because 4 will be somewhere here. Like it can be here. So Q value here. Q value was assumed to be 4. So Q value will be here. If Q is 3, then Q will be here. If Q is 5, Q will be here. So if Q is bigger than 2, then we don't have to look for Q anymore. We just return this root node, so that will be 2. Here, same thing. So if Q is 5, we don't have to search for the right subtree. We just return this root node. Same for this guy. Even though this is less than 2, yeah, we still return the root, because 2 will be the LCA. Same thing here. So that's the main idea for this problem. So if you look at the code here, so the first part corresponds to if both p and q are on the left subtree of the root, then we go to the left subtree. So that's given by root dot left. If they are on the right side, right subtree, then we look for the right subtree. So here we have root dot not, root dot right. Now for this case, like this case and this case, that's given by else. So first case would be when p is in the left subtree and q is in the right subtree. Then we return the root. So there will be 6. If root value is equal to, say, a p value, in this case 2, and then q is in the either left subtree or right subtree, then we return the root. Same for q value too. In this case, we just return the root, and we are done. Yeah, that one will solve the problem. My code, and let's run this. Yeah, so this is the first problem. Let's talk about the second problem. Here the only difference is that we don't have a binary search tree, we have a binary tree. So if you can notice, here we have a 3, that's the root node, but then we have a 1 on the right and then 5 on the left. So that binary search, that unique property of binary search tree, doesn't exist here. Nonetheless, this problem is pretty identical to the previous one. Let's solve this. So p's value is 5 and q's value is 1. Then so they are here. So we start from 3, that's the root node. So we start from 3, we go to the left, and then here we found 5, so we backtrack, and then we search the right side. And then we found q's. So we backtrack again, and then we return this node 3. That's the main idea for this. Now that's the easy case. How about this case? Let's say 5 is here. Let's say p's value is 5, so it's here, and q's value is 4. The way I approach this case would be, you start from the root node, and then you first go to the left. If you find p's value, you backtrack. You don't search the subtree beneath 5. You don't search these trees. You backtrack, then you search the right subtree, and then here you'll be going through all nodes, and then here. So let's look at this. Here, if you from here to here, now we found the p's value, so we backtrack and then we return 3. We return the root. Now we search the right subtree of this node 3. So that will be our third step, and then we haven't found it, so we go to the next step, and then we go to the next. Now here, this dash line and dash circle, this means we have a null. So here, when we are here, it is null, so we return none. So here we backtrack and then we return none. Now we look at the right subtree of this. Here it is also none, so we return none. So we backtrack, we return none. Since both of them are none, so we return none too. So we backtrack. This is step 9, and we return 9. Now we look at the right subtree of this one, 8. Well, we still go to the bottom, the leaf. We still go to the leaf node. Well, since the leaf node for 8 they are both none, so we return none. So that's 12th step, and that's the 14th step. So here, step 12 and step 14, we both return none, and we return none. So step 15, we return none, and now here we are at 1. Since both of these, like here we are returning none from the left subtree, we are also returning none from the right subtree. We are returning none to here. So step 16, we return none, and we are at here. And what do we have? On the left, we have 3. On the right, we have none. Well, because we haven't found the q value. Q value was here, but we didn't search beneath this node 5. So let's say we have a left sub tree is equal to 3, right sub tree is none. If we set left sub tree or right sub tree, what does this give us? This gives us 3. So that's the main idea behind this problem. So yeah, so if unfortunately we have to traverse every single, the worst case would be, the worst case for the time complexity for this case would be O of n, because worst case is we have to look at every single element. But this is the code for this problem. Yeah, if we find p values or q values, then we return the root, and then we don't look further beneath. We don't look beneath that node. We return the root. So that's, and then here we will keep searching, and then eventually we will this null, and then we return none. And then here, the first case, like if left node and right node, this will be this case. The left node would be 3, right node would be 3, so we return this 3. Here for the else statement, we have a left node or right node. So in this case, we will have either one of them will be none, and other will be some root value. So we return that. So that's the idea behind solving this problem. And yeah, you can see that they are very similar. This is my code, and let's run this. Yeah, so that was it, and thanks for watching. Yeah, I'm feeling a little bit better. So hopefully my next video will be much better quality than the last two. Thank you so much, guys, and have a great weekend.